Good morning.
Good morning. So welcome to the last day of the workshop and
All right, here. I know. I got the memo. Yeah. Okay. So thanks everyone for coming back. Really hung in there. Been a long workshop, but in a good way. Right? Okay. We're all a little tired, but because we did hard work. Okay. So just to recap, so we're doing Stein's method for normal approximation. So the first thing what we showed is that the Wasserstein distance between some W and Z, which is standard normal, is less than or equal to the sup over these functions in this class of this expected value of f prime of W minus WF of W. All right. Okay. So this is what we want to bound. And then this class F is with bounded F and F double prime. The sup norms are both bounded by 2, and the norm of F prime is less than or equal to the square root on 2 on pi. Okay. So this reduced the problem here. And then how do we, if we want to bound this thing, we now have to bound the right-hand side, which only involves W, but then how do you do this? And so then to bound the right-hand side, we use this auxiliary randomization. Okay, so what does that mean? Well, we had a few things. Well, firstly, so we had this auxiliary randomization to work on expected value of WF of W. So this was always, we're always trying to sort of get at this in some way, rewrite this in some way with some other, using the structure of W so that we can do a Taylor expansion and find this F prime term. That thing. And so what were auxiliary randomizations? We had this local dependence, which we just wrote, I'll just leave local dependence was one. And then we had exchangeable pairs with the linearity condition. And this linearity condition was really the key thing that allowed us to get at this. And now finally, we're gonna, this was all recap. And now, so today, we're gonna do one more of these auxiliary randomizations. This is one we saw before for the Poisson approximation size bias. Okay. So just recall the definition of the size bias distribution. So last time it was integer valued, and so I defined it in terms of its PMF or whatever. But as I said then, we can define the size bias for a non-negative random variable with a finite mean. we say the random variable XS has the size bias distribution of X if the expected value of G of X of S, G of X size bias is equal to this. So we just take the probabilities of X and we bias them against F. I should say, like, this is for all bounded G. So, you know, this determines the distribution of X sub S because I can take G to be the indicator of being in some set. And so this says the probability that X sub S is in that set is equal to the integral of X over that set divided by mu, right? So it's, anyway, the number of ways to say it. X sub S is absolutely continuous with respect to X, and this is the Radon-Nikodym derivative is X on mu. Anyway, so this is the defining property of the size bias, size bias. And we talked about how to size bias sums of Bernoulli's, which we'll use again. But okay, that's the setup. Now assume we have a non-negative random variable with mean mu and variance sigma squared. And then we have the size bias. We somehow have the size bias distribution, size bias random variable defined on the same space as X. Then, of course, we want to do normal approximation. So we're going to subtract the mean and divide by the standard deviation. And so for W, X minus mu over sigma and Z normal, the Wasserstein distance between W and Z is bounded by this term on the right. This square root of 2 on pi is going to come from this square root of 2 on pi. And then there's some ratio of mu on sigma squared, the square root of the variance of the conditional expectation of the difference of the size bias and the original conditional on X. And then we have this term that's mu on sigma cubed times this squared terms. Okay, so that's the theorem. To prove it, it's not very hard to prove. I guess, you know, canonically we think of X is sort of indexed by n and it's going to infinity. If we think of it as sum of IID random variables, then mu is of order n and so is sigma squared, right? So this is a constant. In generic situations, this will be constant. And so we actually need this variance to go to 0 if we're going to have the bound go to 0. So that's a key thing is this is a little different. In the Poisson situation, we were just looking at the expected difference. We now have a variance and really you need the variance to go to 0. So it's a little bit harder to bound this term than in the Poisson case. Now here we have mu over sigma cubed. So if mu is of order sigma squared, we already have our 1 on sigma, which is kind of the rate we want, right? If sigma squared is order n, then that's 1 on the square root of n. And so really we just need the difference between xs and x to be bounded of constant order. Okay. So that's it. So the size bias. Before we were looking at the amount that the size bias changed from the original variable plus 1. Now we're looking at the size bias minus the original variable, and this will be small as long as that the amount of changes is sort of constant order, and then this variance is small. Okay, good. All right, so that's the. We'll do an example in a second. Let me just prove it. It's quite easy to prove. So here, again, we just work on this expected value of W f of W. So this is the proof of the bound here, and we just write that as the expected value of x minus mu over sigma times f of x minus mu over sigma. And here we have x times a function of x, right? So this is f of x minus mu, but this is also a function of x. So that's what's going to happen here. So this becomes, I'll just put the 1 on sigma on the outside, and we have the expected value of x, f of x minus mu over sigma, minus mu over sigma times f of x minus mu over sigma. Okay, all of that in expectation, that's fine. But now, as I said, this is x times a function of x. Only mu because I put this. Okay, so now we had x times a function of x, and so we can use this size bias. We have x times a function of x, so that is going to be equal to that same function, but now we replace x with the size bias and we multiply by mu. Okay, so continuing over here, we'll get a mu here. We have a mu here, so we have a common factor of mu on sigma. And we have the expected value of f of x size bias minus mu over sigma minus f of x minus mu over sigma. Right? So we get a mu, where this becomes mu times the size bias. Right? Good. Okay, and now we're in business, we can do a Taylor. This is W. And we want to compare this to f prime of W, so we do a Taylor expansion, right? So this equals mu on sigma times the expected value of this minus that, which is xs minus x over sigma times f prime of w. That's what w is, and then plus 1/2 xs minus x on sigma squared times some f double prime of w star. Again, w star is just something between these two. It depends on xs, it depends on x, it depends on everything. That's fine. Okay. Okay, so now right. So that was just the wf of w. We need to compare that to f prime of w. Obviously, we're going to compare this. This is the f prime of w. Then we're just going to bound this directly in absolute value. And this thing is bounded in norm by 2. That cancels with the 2 here. And we get this xs minus x squared over mu on sigma cubed. So that just leads directly to this term, right? Okay. So then expected value of f prime of w minus wf of w is less than or equal to, so I'll put this term mu on sigma squared, xs minus x, we'll compare that to the 1 here. So the norm of f prime times the expected value of 1 minus mu on sigma squared times xs minus x, right? So that's this mu on sigma squared, xs minus x, and the f prime matching there, and then plus times this 1 on 2 mu on 2 sigma cubed times the expected value of xs minus x squared, like that, right? We have, okay, so as I said, this thing's bounded by 2 because it's in our function class, and so that leads directly to the second term in the bound here. And for the first term, sorry, let me put it like this. This should, I need to condition on x. That's okay, we can condition on x here. That's important. Okay. Okay, I just condition on x and w and x are the same. I can pull that out. So I can put it, use the tower property and replace that with a conditional expectation. Okay. Okay, and then now we'll be done. I mean, this thing's bounded by the square root of 2 on pi. That's what we have. And so we'll be done if the mean of this is equal to 1, because then I can use Cauchy-Schwarz and I'll get the square root of the variance of that. And that'll give me my mu on sigma squared on the outside and the square root of the variance of the conditional expectation. So, okay, so now the result follows by Cauchy-Schwarz. If expected value of xs minus x times mu on sigma squared equals 1, right? So if this mean is equal to that, so we can just work that out. So what's the expected value of xs? What's the mean of xs? Well, we can work on the mean of xs because we know how to take expectations against functions of xs. So the mean of xs is when g is just equal to the identity, we get the expected value of x squared on mu, right? But this thing equals the expected value of x squared over mu minus mu times mu on sigma squared. That's what we have. And what is this once we put the mu here? So let me divide that by mu and make that a mu squared. And that's just the variance over mu and mu over the variance. So that's 1. Okay, done. So then that's it. You know, it's just the usual. Once you have this, you sort of just do Taylor expansion. Okay, great. So then how do we use this? Well, I mean, we talked a lot about, I'll just go through this quite quickly because we talked a lot about size biasing. We talked a lot about this example before, isolated vertices. So now we can, what we showed, you know, earlier was that for the Poisson, we looked at the Poisson approximation for the number of isolated vertices in an Erdős-Rényi graph. And we found some regimes where it was Poisson. We found some regimes where it wasn't Poisson, but we thought it might be normal instead because the mean and the variance were growing at the same rate. but not with the same constant. Okay, and indeed we can use this theorem to do this. So just recall the size bias construction. The size bias construction is if we have something that's a sum of Bernoullis, we choose a Bernoulli according to with probability proportional to its mean, and then we force that equal to 1 and we adjust the rest. Remember? So for the isolated vertices, what we did is we chose a vertex uniformly at random. We just erased all the edges to it, and then we looked at the number of isolated vertices after doing that. Okay. So recall if x equals or this is xi, where this is the indicator, vertex I is isolated in an Erdős-Renyi graph. Okay, then x of s equals the number of isolated vertices when erasing all edges connected to a uniformly chosen vertex, which I'll denote as big I. That's a uniform I, right? So now what's xs minus x? Well, we talked about this before, is that what is xs minus x? Well, the only way so I'm removing edges, so I can only isolate vertices. So I can isolate the original vertex if it's not already isolated, right? And then I'm gonna potentially isolate some things connected to it, but the things that are connected to it, they have to be degree 1. They have to only be connected to vertex I, okay? So I'll just write it like this, equals, so I'll tell you what this is in a second, n sub I plus 1 minus x sub I, sorry, that should be a big I, where these n sub I is the number of degree 1 vertices attached to vertex I. Okay, so this is what this is. It's just you can only increase the number of isolated vertices. The contribution is degree 1 vertices that are attached to vertex I, big I, and then plus this thing has to 1 as long as it's not already isolated. Right? If xi is equal to 1, then nothing changes. This is 0. That's okay. So I just draw the picture. So the picture was like this. Here was vertex I. We have some things like that, and then we have a bunch of these guys that are attached to more things, and then so so now I equals little I, and what do? We get this graph like that, and that's what it looks like. And so what we've done is, if this thing's not already isolated, then we isolate it, so we get a contribution of 1 from there, and then all of the things that were degree 1 attached are now isolated, but nothing else can become isolated. Right? So this is the picture. Okay, is that all right? Is that clear? Okay, so now we just need to compute these terms. Maybe I'll just write down the key steps here. So the first thing is, what's the expected value of xs minus x given not x but g? You can always increase the sigma field. So like given the whole graph, what is this thing equal to? Well, I just wrote what this is, but now we still have the randomness of I we need to sum out. All the rest of these things are G measurable, right? Like that, and I can read them off the graph. So this is equal to 1 on n of n sub I plus 1 minus x sub I. That's what it equals. And so what's the variance of this? So we just found the variance of the variance of this, we'll just bound by, well, you have two terms here, you have this sum, and I just bound the variance by 2 times the sum of the variances, right? There's a cross term, but we can use like Cauchy-Schwarz and stuff. So this is less than or equal to 2 on n times the 2 on n squared times the variance of the sum of n sub I plus the variance of, well, the sum of 1 minus x of I, but that's the same variance as the sum of the x of I. That's just variance of W, right? Okay. Okay, and so this is the variance of the number of isolated vertices. This is the variance. What is this term? Well, this is the number of degree 1 vertices connected to I for each I, and now we sum over every I. But when you think about, you have a degree 1 vertex, it can only connect to one I, right? So this is just the total number of degree 1 vertices. Okay. Okay. So these things we computed before. So I mean, actually, maybe I should write this down. Okay, so I'll just leave it like this for a second. But from before, mu equals n times 1 minus p to the n minus 1. And the variance sigma squared was equal to, let me just write it down. We did this calculation. It's somewhere on this piece of paper, maybe. It was equal to mu times 1 minus p to the n minus 1 plus n minus 1 times p, 1 minus p to the n minus 2, like this. That was for the calculation. And then we can do a similar calculation for these degree 1 vertices. So we write this as a sum of indicators that vertex I has degree 1, right? So maybe I'll just skip the calculation. It's, you have to have the covariance. What's the covariance of, the indicator that vertex I and vertex J both have degree 1. And so you have to look at all the ways you can do that. They're either connected to each other and isolated, or they're each connected to something else. You can just write these things down. It's not to, we did a lot of these kinds of calculations. And, basically you get something of the order, let me just write this down. You get n squared p, 1 minus p to the n minus 2, and 1 minus np, 1 minus p to the n minus 2, plus n squared p, 1 minus p to the 2 n minus 2, plus n minus 2 to the p, 1 minus p to the n minus 2. I think that's right. There might have to be, this is supposed to be a covariance, so it's probably minus n minus this thing squared, p squared, 1 minus p to the 2 n minus 2. Something like this, yeah, okay, whatever. It doesn't matter. You can do the calculation. I'm not going to get too much into this. Okay, so the point is, this is an exact expression in terms of n and p for this bound, right? If I combine mu sigma squared, this variance, that variance of W is just sigma squared, then I have an exact expression for a bound, an exact bound for this in terms of n and p. And so that first term, we have some exact bound for the first term in the bound here. So we have an exact expression for this. Okay, I'm not going to write it down. Just showing you it can be done. And then similarly, similarly for this second order term, we know what xs minus x, we have this nice expression for it. And so the expected value of xs minus x squared is just equal to, we do a condition, we condition on g and then take the expectation, and you get 1 on n, I equals 1 to n of the, of n sub I plus 1 minus x sub I quantity squared, like this. And basically this is in 0, 1. And so essentially this is of order like ni squared, right? This is sort of, I don't know, less than or equal to 2 on n times the sum I equals 1 to n of the expected value of ni squared. And ni you can write as in terms of indicators that, how many things attached to I that have degree 1, and you can write this down as well, and you'll get some bound that's like, let me just write the order of it, 2 on n times something like order np 1 minus p to the n plus n squared p squared 1 minus p to the 2n something like this. Okay. Okay, so you can write it anyway. These are just sort of straightforward, but somewhat laborious, bookkeeping calculations. But the point is the whole thing, everything in this bound we just computed completely explicitly. And so you have a bound that's completely explicit in NP. And so that's what we want. And I'm not going to put it together, but I will say as an exercise, you can put it together and you can find regimes where you'll get this normal approximation. So as an exercise, if P is like n to the negative alpha for some alpha between 1 and 2, not including 2, then you can show this Wasserstein bound is the order we want, 1 on sigma, and sigma going to infinity. Okay, so when alpha is 2, the variance becomes constant, so you don't get any normal. So this is just an example where you okay, and then I don't know, there's other regimes you can look at if you want to. So I think an interesting one is maybe the other regimes. What do I say? Say claim P equals C log n on n might be interesting. Okay. For C less than 1. I think if C is bigger than 1, then we're in this Poisson regime where things are constant order. Okay, anyway, this is just to show you can really compute, this bound is quite useful and you can just compute everything you want. Okay, good. Any questions? Yeah.
So, look at orientation, a lot of fixed point, that's also possible. So, kind of problem that was not good,
The number of fixed points? Yeah, so there you'd use exchangeable pair. You can use exchangeable pairs because you can you sample your permutation and then you multiply by a random transposition, and then that gives you an exchangeable pair. So W is your statistic for the whatever you care about the permutation, and W prime is the number of that same statistic once you multiply by a random transposition. Yeah, that's a reversible markup chain on the symmetric group. And so typically for those kinds of problems where you have some algebraic structure, the exchangeable pairs is much better because you can define reversible markup chains. Yeah. So that's usually, size biasing is maybe not so clear. I don't know. For fixed points, you can size bias, right? You can you choose one uniformly at random and then you fix it, and then whatever it was going to before now needs to go to what it went to before, something like that. So there's some similar, yeah. So the answer is yes. The answer is yes, yeah. And there's definitely been some work. Percy Diaconis had some work on this kinds of stuff, and actually my PhD advisor Jason Pullman is very interested in statistics of algebraic structures related to like representation theory of the symmetric group and stuff. So yeah, Stein's method is a quite powerful tool in that setting. Yeah. Okay, other questions? Okay, so that's it for normal approximation. So here's just you have the slides. These are just where you can find more information about this kind of thing. Let's see if I can manipulate this. This one, oh, it's so close. Need to go around the side. There we go. Oh yeah, we need to make it big. Very, very finicky, this black bar. And then we have to click on that first. Yeah. Okay. Is this the right one? Yeah. Okay. So now we're going to go to a third topic, which is concentration inequalities. This is related to large deviation principles, but anyway, we're not going to use that language, and it's a little different. Okay. So what's a concentration inequality? Basically, this is a famous Hufting's inequality. Let's do this by example. So assume we have a bunch of independent random variables and they're bounded They're bounded. They have a lower bound of A and an upper bound of B. And then we look at the sum of those independent random variables. And what we want to do is, we want to say, okay, these things are going to look normal. They're independent, they're bounded. They should look normal, like a normal distribution. So we could have some Berry-Esseen theorem or something for this. But what we're interested in is like tails. So we want to estimate the small probabilities. We want to estimate the deviations away from the mean. And like in particular, we want to know as t becomes large, what's this probability that Wn minus its mean is bigger than or equal to t? And we're interested in when t is large, when t is, bigger than the standard deviation, bigger order than the standard deviation. Okay. Now you might say, okay, we could use the central limit theorem to estimate probabilities like this, but when t is large, those probabilities are small. And we saw the error in the central limit theorem is 1 on the square root of n. So as soon as you're trying to estimate probabilities that are smaller than 1 on the square root of n, the central limit theorem doesn't help you. Okay, so this is a fundamentally different problem because we're trying to estimate really small probabilities. Okay, so the conclusion of Hopfling's inequality is that this probability, these deviations are bounded like 2e to the negative 2t squared over n b minus a squared. Okay, let's ignore 2 and b minus a. Don't worry about those. The key features of the bound is the t squared and the n. So t squared is telling you that these things are decaying very fast, order e to the negative t squared. Of course, we're dividing by n. And you might say, well, that's going to really destroy the bound. But if you think about this, the standard deviation of this is like square root of n, right? And so really, I should be sort of dividing this by square root of n, which is the same as sort of multiplying t by square root of n. And so then this is saying that and this is really saying that a better way to write this would be, I say better way to write it. I mean, I wrote it on the slide, but somehow I'm writing a better way to write it. Okay. Probability that Wn minus the expected value of Wn, is my claim is Wn? Yeah. Greater than, this thing is of order square root of n, so it should be square root of n times t. This is less than or equal to 2e to the negative t squared over 2t squared over b minus a squared, like that. Okay, so then this tells me that this normalized thing that is of order 1, these probabilities are decaying like e to the negative t squared. And so again, t doesn't have to be very large before this is less than 1 on the square root of n for some fixed value of n. Okay, so again, this is just a different regime. Okay, and inequalities of this are really nice because if I take for this t, maybe I should call this s. Used here. So if I take s to be like b minus a over the square root of 2 times the square root of a constant log n, right? Then what is the order of this bound? Then this bound is of order n to the negative c, if I've done this right. And this is just by manipulating this constant, right? So this tells you things that like once I get beyond the standard deviation, the probabilities become minuscule really fast. And this is very useful. Maybe you have a lot of these and you want to do a union bound or something like that. You're going to need something like this to do a union bound if you have an infinite sum, because you need c bigger than 1. You have to choose c bigger than 1. So this is the general idea of these things. Okay, I'm not going to prove this, but we are going to use a very important tool that's the basis of this, well, many concentration inequalities, and that's called this Chernoff method. So I mean, I'm calling it that, but the history of this is quite complicated. These concentration inequalities, these kinds of things were sort of discovered and rediscovered, and it's folklore, and it wasn't made super. So anyway, Kramer was Swedish. He was a Swedish actuary. So if you went to Verdon's talk and he said large deviation started with the the Swedish people, he's one of them. Okay. 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 So let's say we have W as a random variable, and it has a moment generating function, which I'm going to write e to the theta W, and this is finite. Let's just say for all theta. I mean, this is not going to be a problem for us because our examples will be sort of a finite nature. Okay, then For t bigger than 0, we have the following tail bounds. The probability w is bigger than or equal to t is less than or equal to the expected value of e to the theta w divided by e to the theta t. Okay, and the second one is the other tail bound, which is the probability that w is less than or equal to negative t. It's up here. Is less than or equal to the this m of theta times e to the theta t. Oh, sorry, and I should say this is for theta bigger than 0, and this is for theta less than 0. That's important. Okay, so this is the main thing. This was on Verdon's slides. He had this, one of his bullet points was just this inequality more or less, and it's just Markov's inequality, right? So the proof is very easy. I mean, this is why it's not clear who this was named after, because probably many people did it. It's just the probability that w is greater than or equal to t equals the probability that e to the theta w is greater than or equal to e to the theta t, because this is an increasing function. That's it. And then you just use Markov's inequality, and that's just. Okay, that's the proof of 1, and the proof of 2 is the same, but you have a negative, so something a little different happened too. Okay, so that's what you get. Okay, so that's it. And this is the main tool. And so the key takeaway is if you can bound the moment generating function, then you can get a tail probability out of this. Oh, and as Verdon said, theta is a free parameter. So of course, in practice, you use this inequality and then you choose theta, you minimize it. Okay, so let's just do an example. That's a silly example, but let's just say we take a standard normal. Okay, then what's m of theta? Then this is e to the theta squared on 2, right? And so for so what kind of bound? I mean, we just want to see what kind of bound do we get out of this method. If it doesn't give us sort of good stuff for the normal, it's not going to give us good stuff anywhere. And so what we know is the probability that a normal is bigger than t, which is bigger than 0, is less than or equal to e to the theta squared on 2 minus theta t, right? This is for t bigger than 0. That's what this inequality says. And now we optimize over theta. Okay, this is the parabola. And this is less than or equal to, oh, sorry, no. Okay, now we choose less than, it's greater than. We choose theta equals what? T on, what do we want it to be here? T. Yeah, okay, choose theta equals t. Yeah, because this is like theta times theta minus 2t. So we want it in the middle, yeah. So we choose theta equals t, and then this implies that the probability, this is less than or equal to e to the negative t squared on 2. Okay, so that's the kind of, now this isn't totally tight because it's known that, I'd already talked about this a little bit. So Mills ratio says that, in fact, this is less than or equal to the minimum, this thing is times e to the negative t squared on 2 times 1 on t like this, and this is tight as t goes to infinity. So this really is the way the tails decay. It's like e to the negative t squared divided by t. So we lose this factor of 1 on t, but we don't really care because e to the negative t squared is, exponentially decreasing in t, and 1 on t is just 1 on t. So the point is we're not going to get exact sharp stuff because we're missing this, but we are recovering this key first time. And then in terms of large deviations, there's sort of an n in front of here, and then this is a log t, so you sort of don't see these things. All right. I should say it's like a log square root of nt. And so in large deviations, you also don't see this. That's okay. Okay. Just a couple minutes, yeah? Great. Okay, I should say the other ingredient is, I mean, basically you're done with this. You just need some expression for the MGF of this sum, and then the key thing is there's something called Hoeffding's lemma, which bounds the MGF in a nice way for bounded random variables. So I just leave that as a comment. You can Google Hufting's lemma and see what it says, and then you can prove this theorem. Okay, it's just these two ingredients. Okay, so now how are we going to do this with Stein's method? Well, how is this related to Stein's method? Well, the key thing is if I look at the derivative of the moment generating function, then this is the expected value of w e to the theta w, right? So I take the derivative with respect to theta and then kick down that factor of w. And now we've already recapped today. This is, if I call this thing f theta of w, this equals the expected value of w f theta of w. And so all these tools we just developed to get a handle on this thing, to write this in special ways, are now applicable to get a handle on this, and that'll give us some bounds on the derivative of the moment generating function, which of course can lead to bounds on the moment generating function. Okay, so this isn't going to be related to any of the stuff that we've done before about distributional approximation and the characterizing operator, blah, blah, blah. This is really just about all those tools we developed for Stein's method, all that auxiliary randomization can be used to work on this. And so then we can get some interesting concentration inequalities in terms of, these couplings we've been seeing, okay? Okay, so let's take a 10-minute break and then we'll talk about how to do that. Yeah. So with that set up. Yeah. Okay. So with that setup, we can now just state the bound we can prove. So we can do exchangeable pairs, we can do size biasing, you can do local dependence, but exchangeable pairs. So I should say Chatterjee pioneered this approach. Exchangeable pairs is what he worked in, so it's appropriate to look at that one first. But also, there's all these other dependency structures. You can also do similar things. Okay, so let's say we have W as a random variable, does mean 0, and some variance sigma squared. And W prime is an exchangeable pair, which satisfies this linearity condition that we had before when we were looking at normal approximation, right? So the expected value of W prime minus W given W is negative lambda times W for some lambda bigger than 0. And then we also, so this is a key assumption. Another key assumption is that the expected value of W prime minus W squared given W is bounded by 2 lambda, the same lambda here, times some BW plus C, where B and C are just constants. Okay, so there's some this is sort of the strongest condition, the linearity condition, and this condition. So these are the things you have to check. And this last one is just some regularity about the MGF, the existence of the MGF, just various expectations that show up in the proof. As I said, a lot of times we're thinking of finite type things. W is a sum of things that are bounded, and so all of this is just satisfied automatically. But anyway, this is just a technical condition to make sure our expectations are well defined. And under this assumption, then the right tail, the probability W bigger than or equal to T, has this exponential tail bound of T squared C plus BT. So B is not equal to 0. This is not sub-Gaussian because we have this T squared and a T here. And then the left tail is bounded by e to the negative T squared on 2C. So we don't have that problem with the left tail. Okay, so that's the theorem. I should say you can see it immediately, like the what do I want to say? There's some asymmetry in this bound, right? Because this is positive and W has mean 0, right? So somehow, in order for this to hold, you must have some tighter control over the left tail. That's why this is better. I mean, intuitively speaking. Okay, so that's where the asymmetry is coming from. Okay. Okay, so maybe I'll just, before the proof, we'll just do an example to see the kind of thing we can get. So the easiest example is we just take a sum of bounded independent things. These mean 0, and the variance is sigma I squared, okay? And they're independent. And they're okay, mean 0, they're independent, and let's just assume that they're bounded by some constant C sub I. I'll call it C sub I, so we don't confuse with that C. Okay. So now we want an exchangeable pair, but we talked about this last time, yesterday. For an exchangeable pair, what do? You have a sum of independent random variables. You choose one uniformly at random and you resample it, right? So for our exchangeable pair, W prime equals W minus Xi plus Xi prime, where I is uniform on 1 to n, and Xi prime has the same distribution as Xi. Okay, so these are just independent copies. So we choose a coordinate or an index at random. We swap it with an independent copy. Okay, and what we showed from before is that the linearity condition is satisfied is -1 on lambda times W, which implies we can take lambda equals 1 on n in this story. Okay, and then what else do we need to do? We need to check this second condition. We need to look at this bound. So then we can do the expected value of W prime minus W squared given W. This just equals, again, we average over I, and we get the expected value of Xi minus Xi prime squared given, let's do this on X. It's okay to, it's maybe not so obvious here that you can condition on X, but you can So is equal to that. We'll get a bound that only depends on W, so the same bound holds for the conditional expectation of W. So this is what we get. The xi primes are independent, and then this xi is x measurable, and so this equals 1 on n, sum I equals 1 to n. The cross term is 0 because expected value of xi prime xi is 0 because independent of xi. And so then this becomes xi squared plus sigma I squared, like that. And this is less than or equal to ci squared, right? Because we're assuming xi's are bounded. Okay. So then, so we can apply the theorem with b equals 0 because there's no w over here, and 2c equal to the variance of w. The sum of the sigma I squared is just the variance of w plus the sum of the ci squareds. Okay. Okay, and then that gives us, let me just write it down, what we get from that. This just gives us that, for example, the probability that W is greater than or equal to T. Well, here actually B is 0, so the bounds are the same, right? Is less than or equal to xp of negative T squared over 2 times the variance of W plus the sum of the ci squareds. Right? Okay. So this was lambda here, so that's where the lambda's going there. Okay, so this is maybe, so what do I want to say? Somehow this is like if the variance of W is order n, this is sort of what we saw in Hupting's inequality, more or less, were these things. And so it's a slightly worse bound because we have this variance added, but it's the same quality in general in terms of the up to the constants and the order of this thing. Okay, but as usual with Stein's method, it's like the point isn't to get the best thing, although sometimes you can get the best thing. In the independent case, the point is that this is going to be more generally applicable. And so we're more interested in cases with dependence when this whole where Hupting's inequality is possible, or dependence that's maybe not martingale dependence. Okay, so let me just I just sketch out the proof of the bound, just to give you a flavor of how this works. So, so remember what we're going to do is we're going to use this Kramer-Chernoff method that I just erased. We just need to bound the MGF. So we want to bound the MGF M of theta. Okay, and we do this by writing M prime of theta equals the expected value of W f of W, where, I mean, this is really an f theta of W, but I'm just suppressing it, where this is e to the theta W. So think of theta as fixed, and we have this thing. Just don't have to carry it around. So the linearity condition gives you that this is equal to -1 on lambda times W prime minus the expected value of W prime minus W times f of W, like that. That's just because if I condition on W here, that goes away. I get the expected value of W prime minus W given W, and I get a negative lambda, and that cancels here. And so I just get back to here. Okay, that's just the linearity condition. And then exchangeability. Exchangeability says that I can, the expectation of this is the same as if I swap W and W prime. So I get an FW prime, and then I have W prime, W minus W prime. And so this is equal to, I'll put a plus here, 1 on 2 lambda, the expected value of W prime minus W times f of W prime minus f of W. Okay, sorry. Like that over a little clearer, f of W, like that. Okay, so this term minus f of W times that is what's there, and this is the term where I swap the order of things. And then this becomes W minus W prime, and that's W prime. Okay. Okay, so that's what we have. And so now let me write this in so let's write this m prime of theta equals 1 on 2 lambda times the expected value of w prime minus w and e to the theta w prime minus e to the theta w. Okay, and then we can use convexity. You know, basically convexity gives us a little convexity calculations of the exponential gives us that e to the x minus e to the y over x minus y is less than or equal to 1/2 e to the x plus e to the y. Okay, so that's a little exercise to show, but this is true. Uses the convexity. And so then we can now replace this. We move this over here and we have w prime minus w, and that'll become a squared, and then we'll get a plus here, right? So we have so we have 1 on 4 lambda times the expected value, w prime minus w squared, e to the theta w plus e to the theta w prime. This is what this gives us. And now we can use exchangeability again. And when we use exchangeability on this becomes an e to the theta w, and this stays the same. So this is like 2 copies of it with e to the theta w replaced, right? Sorry, I missed a theta here. This should be theta w prime, and this should be theta w. So there should be a absolute value of theta here. So it was theta. The argument here is this is x. Just put that there. Sorry about that. Okay, and then exchangeability again says that this is equal to, by exchangeability, theta on 2 lambda times the expected value of w prime minus w squared e to the theta w. And now we can use this third bullet point here, that expected value of w prime minus w squared given w is bounded by that. So we condition on w, the MGF comes out, and we have all we're left with is this conditional expectation squared. Okay. So then this is less than or equal to, by the third one of these, 2 lambda, the 2 lambda cancels, bw plus c. Okay, but then now we have a w e to the theta w, we have the e to the theta w, we get m prime and m back, right? Okay, and now I'm not gonna. I mean, this is the key thing. Now we have this inequality. There's a bunch of things you have to look at, like m prime of 0 equals 0 because that's the mean, right? And the mean is 0. You know, m prime of theta is greater than or equal to 0 if theta is bigger than 0, and less than or equal to 0 if theta is less than 0. So you have these kinds of properties. And so we break this into 2. You have to break it into 2 cases because of this. So when theta is bigger than 0, you get stuff like, you know, m prime of theta divided by m of theta is less than or equal to theta c over 1 minus theta b. So you can this is important when you're sort of dividing stuff. But anyway, this is so again on this side we had m prime of theta. So we subtract that, we get this 1 over theta b, 1 minus theta b. That's where that's coming from. You divide it out, and then you have a theta times c. Okay, so you get these kinds of inequalities, and then this tells me that d theta of log m of theta is less than or equal to theta c over 1 minus theta b. Okay, so I'm going to skip the details, but then you optimize this where you can bound the log of m of theta, and when theta is 0, this is 0, or this is 1, and so the log is 0, and then you have a bound on this, and what you end up with is this is less than or equal to e to the c theta squared over 2 times 1 minus b theta. Okay, and then you use this Kramer-Chernoff bound is the rest. Okay, so this is really the key thing. Once you have this, you're in business. Somehow the proof is easy, but there's some real ingenuity here in thinking of how to do this, right? It's not. I mean, the recognition that you can use Stein's method here is maybe something that would come, but then getting the right conditions and everything, and getting this all working, and the convexity is it's very clever. Okay. Okay, so that's it. I'm just going to leave it at that, and then you can do similar things to get the other tail bound and so on. So all of it looks pretty similar to this, because I want to do more stuff. I want to get to the applications. Okay, so I have two applications, but I've short 20 minutes. So maybe I'll just do the more interesting application, but you can take a look at the other slide, and it's a little easier as well. Okay, so let's do this application of the Curie-Weiss model. So what's the Curie-Weiss model? So this is a model of magnetism, or Boy model of magnetism. So you imagine you have some lump of atoms, and each one has a spin up or down, or a north or a south magnetization, right? Orientation, and we encode that as a +1 or a -1. Okay. And the total magnetization of the whole thing is the sum of all those spins. Okay, and we divide by n, so that this is a -1, 1. And the idea is if you're very close to 1, then all the spins are 1 and you're magnetized north. And if all the spins are close to -1, then you're magnetized south. That's the basic idea. Okay, so this m of sigma is some measurement of magnetization. Okay, and then we're going to put a probability measure on these spin systems. And there's a parameter beta, which is called the inverse temperature. You think of high temperature as beta small and low temperature as beta large. Okay, and this probability measure is given by this, the probability that I choose a spin sigma is proportional to e to the n beta over 2 times m sigma squared. Okay, so again, this is sort of constant order. It's in -1, 1, and we sort of blow this thing up by n. I think Veridon talked about that a little bit in his talk about that this is the right scaling to get something to have some effect. And then the parameter beta is here. Okay, so when beta is equal to 0, this is just the uniform measure. I'm just tossing a coin of 1/2 independently for each spin. Okay, and as beta becomes larger, the effect of the magnetization becomes larger. It puts more and more weight on magnetizations that are closer to +1 and -1. All right. Okay, so that's the model, and the reason the model is interesting is because as you vary the temperature, when beta is close to 0, this thing kind of looks like independent spins, and when beta gets above 1, it doesn't look like independent spins at all, and in fact it sort of concentrates around 2 points, one positive, one negative, and those points aren't 1 or -1. Okay. And so there is a sort of phase transition around beta equals 1 when the temperature is equal to 1, where you go from sort of things like it's behaving like an independent system, and then the temperature gets too low and it starts to freeze, and you actually see this magnetism. All right, that's the basic idea. Okay. Okay, so the story is that if I sample this thing, x according to this, these are the spins now, that's in ±1 to the n, and I call big M the magnetism of my sample from P beta, then these things concentrate, the magnetism concentrates around hyperbolic tangent of beta times m, and that does it at a scale of t on the square root of n. So once again, you want to think, in fact, this thing is going, because the way we scaled everything, just think of this as a law of large numbers type scaling. This is going to be close to 0, so not close to 0, it's going to be close to these points, but the fluctuations of order 1 on the square root of n. So that's why this t square root of n. This beta on n is smaller order. Just ignore that for now. I mean, just think of this as t on square root of n, and that's the right scale. Like this should be 1 on the square root of n, and we want to know what the fluctuations look like on that scale. And what you get is that they're bounded by e to the negative t squared, basically, of physical. Okay. Okay. Tan. Oh, yeah. Both are random. Yeah. Okay, but I need to explain more because this is confusing, what's on the slide. So let me let me explain more what's happening here. We may not even get to the proof of this. I might just tell you what's happening here. See how much time we have. I mean, okay, the proof uses the exchangeable pair, and the exchangeable pair comes from Glauber dynamics, and I'll try to explain that. But I think it's important to understand what's happening here. So the first thing, yeah, so the interpretation here. So M, this magnetism, is concentrated around the solutions of alpha equals hyperbolic tangent of beta times alpha. Okay, that's the way to say it. It's concentrated around the solution. So we need to understand, the first thing we need to do is understand this equation. Okay, so here's the picture of the graph of hyperbolic tangent of beta alpha. There's two things that happen. When beta is less than or equal to 1, what happens is yeah, so here I'm on negative 1, 1. So what's happening with hyperbolic tangent? Hyperbolic tangent is going to look like this, okay? But the key thing is we're comparing this to the line. This is the line, this is the alpha line, and this is alpha equals alpha. And we want to see what are the fixed points of this thing. So now it's sort of like if we come in here and we go up, like we can have 2 fixed points, or we can come in here and just squeeze through and we only have 1. And that's exactly what happens when beta is less than or equal to 1. The picture looks like this. And this is just, you just look at the derivative at 0. When you get the derivative at 0, this is beta. Okay. So this is tanh beta alpha, and this is the slope at 0 of this is beta. So when beta is less than 1, it starts up here and it comes in kind of shallow way. And even when beta equals 1, it just touches it and goes. Okay. So there's only one solution. So one solution at 0. Okay, so then this says this is the high temperature regime because this is the inverse temperature. Okay, and then what happens when beta is bigger than 1? Well, it's a similar picture, but now we're going to have 3 solutions, right? So beta is bigger than 1. It looks like this. We come in, and we have to come like that. Okay, not the best picture, but anyway. Now there's 3. It should be symmetric, for example. But anyway, there's 3 solutions now. Okay, and this is the negative of that one. So those are the 3 solutions. Okay, so then, so what it's saying is that when beta is bigger than 1, there's 3 solutions of this, and that M will concentrate around all 3 of these. Well, some subset of these 3 solutions. Okay, as it turns out, it's not going to concentrate around 0, so something's going in this case. But so let's do a little bit of the analysis. So this is like sort of, in Veridon, we're talking about entropy. During these calculations, is kind of the calculation you do to understand these kinds of systems. So we can just write, like, what's the probability that under beta that this M of X equals some alpha n over n. Okay, so this is, sorry, the alpha n over n should be like that. It should be some alpha n. This is something of order n over n. Well, that's just proportional to what? That's the number, the size of the sigma, where m of sigma equals alpha n over n, the number of those things, times the probability that this occurs, which is ext of n beta on 2 times alpha squared. Something roughly alpha squared, right? This is approximately equal to alpha, right? The whole thing. Up to discretization is alpha squared. Okay, and then, this m sigma was the sum of all the spins divided by n. So this is just the number of these things where I have a pluses and minus ones where it sums up to alpha n. That's just some binomial coefficient, right? Because I need, okay, it's +1, -1, but you know what I mean? I need some number of ones and some number of minus ones, so I can sum that. And then I have I have how many ever number of plus ones, I have n choose that many ways of putting them in. All right. Okay, so then you can use Stirling. So this is some binomial coefficient that you can write down, and then you can use Stirling's formula for large n. And what you get is that this thing is asymptotically equal to exp of n times beta alpha squared divided by 2 minus this sort of entropy. Maybe I should drop a few logs and change some of the alphas to U's or something to match Verdon's slides, but I think maybe that might be confusing. So it's something like this. Okay, and then there's one more. Let me put a square bracket here, n times that thing. Okay, so this is what you get. This is just coming from here, and this is coming from this. This is just this Bernoulli entropy, right? That's all that you're getting here. So that's what he's talking about, this entropy. You have to look at the entropy. Here's the entropy of the kind of base measure, and then you have this thing here. All right. Okay, and then you want to maximize this, right? Because somehow this thing, if this thing's going to concentrate, it's going to concentrate around these most likely configurations. I should say we can just plot this thing at this point, but I'll do that in a second. Okay, so then if we want this to concentrate, we want to maximize. So maximize. So we take d alpha, right, of this d alpha of this expression, the expression in this expression of the square expression. If we want to maximize this, it's enough to maximize this term in here. Okay. And because we have this e to the n, whatever the maximum, we're really going to see this. You know, it's going to blow up. Okay, and then dd alpha of that is equal to beta alpha plus 1/2 log 1 minus alpha over 1 plus alpha, and you set that equal to 0. And that gives us the critical points. I mean, not all of them necessarily at the maximums, but that'll give you the critical points. And so then, okay, so now how is this connected to any of this story? If alpha equals the hyperbolic tangent of beta alpha, then this is satisfied. Okay, then log of, you just compute log of 1 plus alpha over 1 minus alpha, and this is equal to log of 1 plus e to the beta alpha minus e to the negative beta alpha over e to the beta alpha plus e to the negative beta alpha divided by 1 minus the same thing. And you simplify, and what you'll find is that it's equal to 2 beta alpha. Okay. There's some e's in there, there's some cancellations, nice cancellations happening, and when you do this, so it satisfies this equation. So these fixed points are exactly these critical points. Okay. Okay, and then we can go a little further and say you can actually I could go here and just write down what's the histogram of this thing, right? I mean, I've just got the likelihood in my hand right here. What's the histogram look like? And the histogram is so now we can do the histogram. So when beta is less than, okay, let me do less than, when beta equals 1, you know what, it still looks like this, but you can't tell by eye. Okay, when beta equals 1, it looks like this. Here's -1, here's 1, here's 0. It concentrates around 0, and it even looks like a nice normal curve. And these standard deviations here, this is for the m, this is for the magnetization. This is of order 1 on the square root of n. That's what I was saying. So it looks like a normal distribution. It's actually one of the exercises for the normal approximation is to show for this model when beta is less than 1 that this magnetization is approximated by a normal distribution. It's very similar to the calculations to do this. Okay, and then when beta is bigger than 1, okay, what happens here? So now we have 3 solutions to this equation. Here's 0, here's one solution, here's another solution, and what this looks like, let me give myself a little space here. It looks something like this. Something like this. Okay, and actually, as n becomes large, these actually it looks more like this. As n is large, so this is large n. And so it's a mixture of two normals that are centered around these 2 points. And in fact, this is so this one, the 0 is a minimum. So in this result, it's kind of a little, it doesn't tell you in the high temperature regime, it doesn't tell you that 0 is not included in this, but it's kind of a neat result in that it does say that in the high temperature regime, you're going to concentrate around either here or you're going to concentrate around either there. And that's one way to capture that. Okay. So that's the story. Sorry, these should be the same height. This height is the same height. Okay. All right. Good. Okay. So I have 10 minutes. 10 minutes. Is that right? Yeah. Okay. So what can we do? So I kind of want to prove this, but it's not quite enough time. So I'll just do part of some of the proof. So the first thing we need is this kind of mungy. We basically need a remainder in this. I don't know. This is the way Chatterjee wrote it, so it's the way I wrote it. But up here, before we should allow for a little remainder here. If we allow for a little remainder here, you can do something. So here's one way of saying you're going to allow for a remainder. It's a little complicated, but he had other applications where using it in this form is the right way. So it's okay. Okay, so here we're going to have x prime is an exchangeable pair. That's going to be Rx. Big F is going to be takes 2 arguments and it's anti-symmetric, meaning when I sweat the arguments, it becomes negative. Okay. And then little f is the conditional expectation of big F of the exchangeable pair conditional on X. And then so that's sort of going to be the linearity condition type thing. And then F prime, the conditional expectation of F of X prime minus F of X times this big F, conditional on X has to be bounded by 2b F of X plus 2c. And then we have this moment condition about these moments existing, this moment generating function. And with that, you get the same tail inequalities we had before for W. You think of little f of X as W, okay? The same ones, okay? So little f of X is W. And I should say, if you want to get back to what we had before, then so the previous bound was just the previous result was f of X. Well, so X is, yeah, f of W prime equals W prime minus W over lambda or 2 lambda. Let's just say lambda. F. So, and then f of little w equals w, f of w equals w. Okay, so change the x's to w. We don't need the w. Okay. Anyway, the proof is really, if you can do the other proof, you can proof there's nothing. It's just a slightly different setup to, okay. So now we want to find an exchangeable pair for this Curie-Weiss model. Like luckily, you see the problem with these Curie-Weiss models, these statistical physics models, is you have this denominator. Like I said, I told you it was proportional to, but there's a denominator there and we don't really know what that denominator is. So even computing things like the mean is difficult. Well, okay, this one, the mean is okay because it's symmetric. But anyway, even computing moments can be difficult because you don't know what the denominator is. Luckily, probably everybody in this room knows if you don't know what the denominator is, there's still ways to create a reversible Markov chain, right? You have the Markov chain Monte Carlo, Gibbs sampling, Glauber dynamics. These are all sort of the same thing. So that's what we have. So okay. So X is distributed according to P beta, and we generate X prime according to Glauber dynamics, which you can think of as a Metropolis-Hastings type thing. Gibbs sampling. These are all in this setting. They're all basically the same thing. Okay, and so how does that work? So we choose I uniformly. We choose a site uniformly at random, and then so given I equals, sorry, dots I equals little I, we resample xi conditional on the rest. xj where j is not equal to I. Okay, and then that resample. Let's just say we sample xi prime conditional on that, and then x equals, we just replace the ith one with that. Okay, so does that make sense? Okay, so let's so to save a little notation here, so the way to say this is the probability that x prime equals I'm going to write little x I1. This is x with a 1 in the ith position. So given x equals little x and I equals I, so given we started from x and we sample this little x and we sample the ith one, what's the probability we resample that as a 1? That's just equal to the probability that x equals xi1, little xi1, divided by the probability that x equals little xi1 plus the probability that x equals xi minus 1. Okay, that's what these probabilities are. So that's all it is, because this is the probability of getting 1 conditional on the rest, and then this is the probability of seeing the rest, right? This is the probability of getting a 1 in that, and the rest are the same, and this is the probability that the xj's are what they are for x, right? That's all it is. Okay, and this is great because this is the ratio of probabilities. The normalizing constant doesn't show up, and so you can write this down, do some calculation, and you can write this as, basically you can write this as, I mean, there's a number of ways to write it. exp of beta, I'll write mix divided by exp of beta mix plus exp of negative beta mix. Okay, like this, where this mi is, it's the same as the magnetization, but I subtract off the ith term. Okay, so we leave out the ith term, because the ith term is somehow encapsulated by this minus here. I mean, the idea is we have this m of x squared, but all of them are the same unless they have the ith one in it. And then when the ith one is in it, it's a 1 or a minus 1. And so there's all this exponential cancellation. Okay. 3 minutes. Can do it. Almost there. I mean, I just need to tell you what the f is, and then the rest is just calculation. So then, so now we said f of x prime equals the sum, equals 1 to n of xi minus x, xi prime minus xi. So we just take the differences of these things, and then the expected value of xi prime given x. So that's what we need. We need this thing. What are we actually studying here? We're about to learn what we're about to study here. So here we have a minus 1 on n. Oh, I should do it this way. Okay, that's fine. Xi minus xi prime. So this is the magnetization here. So okay, so I should say that we have this sum I equals 1 to n, expected value of xi prime minus xi minus xi prime. That's going to be the same unless I choose that one, right? So we get a 1 on n times the sum of xi minus 1 on n times the expected value of xi prime given x next, like that. Sorry, there's a sum here. And then this thing is, you can write it down. What's the probability this equals 1? It's over here. Probability equals 1 minus conditional on x minus the probability it equals -1, right? So you have to do this. But anyway, when you do that, you'll find that this is equal to the hyperbolic tangent of beta mi of x. So that's what it's equal to. So it's just a little calculation. And so this is m of x minus hyperbolic tangent of beta mi of x. Okay? That's not what we want. We wanted our little f of x. So that's what our f of x is. We want our little f of x to be just the magnetization minus tangent of beta m. But actually, this thing is only off by 1 on n from the magnetization. So we can replace this by tangent of beta m at cost of beta on n. Why is that? Because tanh is Lipschitz. Okay, so that's where this beta on n comes from, is that little bit. Okay, so, and then I'm out of time, but showing this thing is true. Let me just write down what the b and the b is 0. So then, so for the final thing, you just get b is 0 and c is equal to 1 plus beta on n. Okay, so you still have to show this, but once you show that, you plug everything in and you'll get the result. Okay, yeah. So I'll stop there. I'm out of time.
That brings us to the end of Nathan's talk. Of course, we still have more from Tom and Newmark. It's a great pleasure to listen to you. Questions? You'll be around for a while more. But she wants to do. So we have two things in it. We do good and you can sit on the big ones.
Okay, all right. You're not going to do it to me physically on this stage. No.
So, governmental forces involved in China. The slides on the pop-up folder, please sit down. Okay. So, please upload a slide. Upload a slide back. Upload a slide back. If you are comfortable, right? Or you want? Okay, upload a slide. So we have we have we have prizes for people who prizes and then that means only a topic. And the title of secret, no one's supposed to know there. We know that, very important. The first prize of the so this one is also an inspiration. What suppose the piano session, he missed his slide, and he came to tell me. Yeah, the first of the prize. This was designed that for the ideas would have this after ideas we have to do virtual problems. But this one is like anything I think before that. That's about the first prize. There are 2 positive prizes. The 2 positive prizes are one person who told us that even if you read books, you can say. Also, please cover. And the third positive prize is equal to that you have a whole next thing we do is we hold this first and you take curve. If you have not like it's like it counts. So and maybe the I want more than people, okay? So when you are, did you ever go on exercises? I don't know what exercise. Extra gift, you have to put it in. No, that's long. Big life. The last one before I go. The last thing before I go for coffee. You will get my coffee to good time. You know, turn thinking about a company back for the sport. I'm ready. There's just like every year, like a 190 or like uh, like 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 so that's when like the like after the cyber yeah.
So today I want to tell you about the tensor analog of the GOE. So remember last time we looked at this uh, Gaussian orthogonal ensemble. Right, so it's a matrix whose off-diagonal entries are independent Gaussians, standard Gaussians, and diagonal entries are Gaussian with variance 2. This is the Gaussian orthogonal ensemble. So this particular choice of this parameter, this variance parameter on the diagonal, that allows you to write the joint density of the entries. This is the joint density of the entries. Okay. So this is proportional to the Frobenius norm squared. Okay. We have a very nice form from the joint for the joint density of the entries with respect to the Lebesgue measure on the on the product space of all these dependent random variables. And as I was saying, so this allows you to an explicit computation of the joint density of the eigenvalues of this matrix. Only in a handful of random matrix models you can do that. So this is one of those models, right? So there is a tensor analog of that. That's called Gaussian orthogonal tensor ensemble. Okay. Again, so I'll just define it as the I'll just define the joint density. The joint density is given by, so let G be a symmetric tensor. Symmetric tensor, real symmetric tensor. So I will say that the order is R as for our convention. And so the joint density of the entries is proportional to -1/2R the Frobenius norm squared. So this is the tensor Frobenius norm that we have defined. Okay. Again, this is a joint density. Unlike the previous case, you would no longer have any formula for the joint density of the eigenvalues, but this still allows you for some things that you'll see. So So this is an exercise for you. So that particular choice of the variance on the diagonal entries that allowed for this expression here. So an exercise is, if I give you a tensor following this density, what is the the individual entries would be standard normal random variables, mean zero, but what is the variance? So exercise G I1 to IR, they follow normal zero. The variance is this R over the number of permutations of this multi-set I1 to IR. Okay. So just as an example, if you have 1, 1, 2, right? That follows normal 0, 3 over how many permutations of these are there? Uh, 3 over 2 factorial, right? So 1, 1, 2. So 2 of them are equal. 3 factorial over 2 factorial, sorry. And 1 factorial, whatever. Sorry, miss the factorial sign, sorry. Okay. So in general, this is the covariance. I just try to work it out. So for this, I want to. So last time I advertised this result for the contractions of Gaussian tensors. So this is actually for this ensemble of tensors. Take G from this GOT. You'll say that such a tensor follows. We'll say that such a tensor follows with GOTE parameters R and N. Okay. So if G follows GOTE R and N, and W is a unit vector in dimensions, and let's look at this contraction. Okay. Pure direction contraction. Then in fact we can say a lot about the spectrum of this, and the techniques are very similar to what we did for hypergraphs, but I'll show you some beautiful, I wanted to show you some identities, so that's why I'm writing this. So let me just write down some results here. So the spectral distribution of R minus 1 over R times Mn. So this converges to the semicircle law, the standard semicircle law. Okay. For hypergraphs, we had this constraint that R was the order of the hyperedges, so R was necessarily less than N. Here R can be much larger. R can be, for instance, N square as well, right? And again, you see this phase transition. So edge eigenvalues. So lambda, am I missing an N here? I think I'm missing an N here. square root of n. Square root of s. And define theta r or delta r to be 1 over square root r minus 1, square root r minus 2 plus 1 over square root r minus 2. Then the largest and the second largest eigenvalue, they exit the bulk of the spectrum, just like for hypergraphs. Okay, so they converge to delta r minus delta. Okay. So you mean this is n? Okay, sorry. So then I don't. So delta r is this constant depending on r. Okay? R is bigger than or equal to 3. And you can check that for r bigger than or equal to 3, this exits the semicircle that you get here. Yeah, the bulk of the spectrum. So if you plot the histogram, it will look like there's like peak outside the bulk of the spectrum. Yeah, so this was something that this is also true for hypergraphs, but here you can also say something about the fluctuations around those limit values. So at r equal to 3, you have n to the 2/3 minus 2. That would become 2 if r equals to 3. Is that correct? Or 2 by root 3 maybe? 2 by root 3. No. Root 2. Is it root 2? Yeah, root 2. Yeah, so this converges in distribution to some random variable. Yeah, so this is a this is a description. This is I think the largest eigenvalue of a stochastic area operator. So there is some description of this. But the point is that you have this n to the 2/3 scaling for the largest eigenvalue. On the other hand, for r bigger than or equal to 4, you have Gaussian fluctuations. So in fact, in this case, we can write down the joint fluctuation of the largest and the smallest. So lambda 1 mn over square root n over square root n minus delta plus delta r. This converges to a Gaussian, bivariate Gaussian with mean 0. And this is the covariance matrix, r minus 3 over 4 times r minus 2 into r minus 1. Okay. So not only the limits are different, the fluctuations are also different. For r bigger than or equal to 4, you have square root n fluctuations and Gaussians, and otherwise you have n to the 2/3 fluctuation. For the random graph, which is r equal to 2, So this is the right endpoint of the semicircle law. In this case, this converges to the Tracy-Widom distribution. Okay. So these limits are different. This lambda 0 is not the Tracy-Widom distribution, although you have n to the power 2 such type fluctuations. Okay. So this type of limits first obtained by Ryder and Virag as a when they are studying the stochastic area operator. So this is somehow a very interesting model in the sense that it produces this limit out of the blue. Okay, at r equal to 2. Uh, yeah, so this is like an interpol. There is a family of laws of that stochastic, the eigenvalues of the solutions of the stochastic area equation. So you can think of this as an interpolation between the Tracy-Widom density, like it's a family of, but this is not exactly Tracy-Widom. Okay. In fact, you can also something interesting happens. So you can look at the largest eigenvector of that matrix and ask if that contains any information about the contraction direction W. Just like the you see in the rank 1 spiked Wigner model, you had a spike direction contaminated by noise, and you were asking whether you can recover this direction, interesting direction. So this is still like a null model, but you can still ask whether there is any remnants of that W there in the largest eigenvector, largest of the smallest eigenvector. That can also be computed, and something interesting happens. So, let S1 and S2, S1 and Sn denote the largest and smallest eigenvectors of this contracted matrix of or Mn. Okay, so if R is fixed, then you can show that there is some information about the contraction direction W in the space spanned by these two eigenvectors. Okay, so the distance between this W and the space spanned by these two eigenvectors, this converges to some non-trivial constant, which is less than 1. Convergence in probability. Okay, so the number, let's see, what is the number? Square root r minus 2, I think. Yeah, the 1 over square root r minus 2. Okay. And in fact, if r equal to infinity, then you can also show that this distance goes to 0. So this will be a perfectly aligned to the space spanned by S1 and S2. So this goes to 0 in probability. The question is, can you recover this W? I know that it lies in the span of W S1 and S2, so it's so maybe in this case, so maybe it's a linear combination of them, but can you recover the coefficients? It turns out it is going to align with one of these vectors. You don't know which, but it will align with one of these vectors. Okay, so if you look at the alignment between these two, okay, then the max of these two alignments will go to 1. Okay, so one of those vectors will be perfectly aligned with this W. But so you can do an histogram, but it's really one of those vectors. You cannot tell which one of them. So certain of the time it will get aligned with this, and certain fraction of the time it will get aligned with this. Okay. R is like Rn. R is growing with N in some way, somewhere.
But it's an odd.
Yes.
But when you want to odd, that's.
Yeah, so that's a different result. Yeah, yeah. You cannot conclude from here. That's a different result. So this is kind of interesting in the sense that okay, so this result that W aligns with one of these two vectors, this is only valid when R is going to infinity, but at a faster rate, at a slower rate than N. Okay, in that case, W will align with one of these two vectors. But at N, something interesting happens. But if R is much bigger than N, then W aligns with either S1 or Sn. Okay. And when W is like, or when R is like growing proportionately with N, then these alignments become random variables. So we always they are in some they're in that space spanned by S1 and S2, S1 and Sn, but we don't know what is the exact combination. Right. So how do we prove these results? And there is another. Okay, so let me mention another result. So one of you asked last time about the Kesten-Mackey law. So somehow the Kesten-Mackey law shows up here. So directional spectral measure. So we have defined what is the spectral measure. The spectral measure is this a measure that puts mass 1 over n on all of the eigenvalues. The directional spectral measure basically weights this point masses in a different way. So I fix a direction x, then the directional spectral measure is given by the weight given to lambda I is given by the energy of the eigenvector in the direction x. Sorry. So this squared. So the directional spectral measure also contains information about the eigenvector. So somehow it appears, it turns out that if you look at the directional spectral measure of this matrix in a direction x, that converges. So let's say x and w have a limiting alignment rho. Okay, rho is maybe a bad notation. Gamma. Then the limiting distribution is a mixture of a bunch of measures. You get the semicircle law with variance r minus 1 over r minus 1. You get, but there is a surprisingly a component which is exactly the Kesten-Macke law. So what is the Kesten-Macke law? Kesten-Macke law is the limiting spectral distribution of a random regular graph. So somehow, so we don't know any interpretation, how to interpret this. Somehow the Kesten-Macke law show up if you look at directional spectral distribution, limiting spectral distribution of those contractions. We don't have any phenomenological explanation of why this happens, but it would be really nice to understand why this is going on. This is the Kesten-Macke law. Which is the limiting spectral distribution of random regular graph. Sorry? Yeah, you have to analyze the Stieltjes transform again. And the Stieltjes transform, basically, what turns out, you can do a partial fraction expansion, and one of the two terms correspond to the Stieltjes transform of the Kesten-Macke law. Yeah, but I don't have any more interpretation than that. Yeah, it's yeah, mu A. So these are the eigenvectors. So A I am writing as ui transpose, right? So you are weighting the point mass at lambda I by the energy of the eigenvector in the direction x. Okay. U1 in that notation, U1 and UN would be S1 and Sn. Yes, this is a generic notation for random matrix. Yeah, in a direction x, then if you take the limit, you get the semicircle law like that with a fraction. What is the fraction? The fraction is the alignment of this x with the contraction direction w. Right? There are 2 point masses which I haven't written down here, and somehow the LSD of the random regular graph also shows up in the mixture. Okay. Okay. So how do you prove these things? Last time we already saw some of the techniques, so I'm not going to repeat those. Basically, an analysis of the Stieltjes transform. But let me show you one of those identities I was talking about. So let Mn be this matrix. Okay. So the claim is I can write Mn as Mn is equal in distribution. So you can explain the covariance structure by this ansatz. Okay. So Z is a GOE and U is normal 0, 1 and V is a standard normal vector of dimension n. And these are all independent. Okay. So once you have this representation, you can just do what you did with the hypergraphs. For the fluctuation, you have to work a little more, but you can derive this. But how do you guess this ansatz? So let me show you one cute computation here. So what are those numbers? Let me also write down the numbers. So alpha is square root r minus 2, r minus 3 over r minus 1. Beta is this and theta is 1 over square root r minus 1. Okay. U is just a standard normal random variable. Okay, so you need one standard normal vector and the GOE matrix to explain it. So let us do a so basically what you have to do, you have to compute the covariances of any two entries of this and check that that matches the covariance that you get out of this ansatz, right? Let me do one variance calculation which is quite cute. So let's do variance of MNIJ. Okay, let's compute it. So by definition, you see the GOT, the entries are all IID, not IID, independent normals, but up to symmetry, right? So the variance turns out to be this sum. Right, so you just write down the definition of this is a sum along the rest of the all but the last the first two directions. Ij, I3 prime, IR prime. And then you have this WI3, WIR, WI3 prime up to WIR prime. Right. So a priori, this is some complicated multivariate polynomial in the entries W. Yeah, so we basically got that and tried to simplify it further. We were unable to do it. And then we put it into Mathematica and it sort of simplified it and gave us a degree 4 polynomial out of this object, right? So then looking at that, we found out why it's a degree 4 polynomial. So let's see. So let's plug in the variance here, right? So these two are uncorrelated unless these two multisets are the same, right? Because we only have the symmetry restrictions, and that so this would be the same only when these two multisets are the same. So therefore, I can write it as I3 to IR. If these two are the same, you get the variance of that entry, and the variance is given by this. number of permutations of this multiset ij, I3 up to IR. And how many such multisets are there which are equivalent to this? You already have ij, so you have to basically permute the other entries, right? So total number of sets that are equivalent to ij, I3 to up is just the number of permutations of I3 here. Okay. And you still have this Wi3, but now they are equal, so you get Wi3 square up to WIR squared. Okay. Now now we can substitute what the numbers here, but the point is some of these I3 to IR, they will also have copies of I and J in them, right? I and J are fixed. I'm trying to compute the variance of the ijth entry. Some of these I3 to IR will have copies of I and J. We will write it as a sum over how many copies of I are there, how many copies of J are there. There are at most R minus 2 of them. And so you have to basically pick which one of those are I's or J's. So you get R minus 2, choose Li, and then R minus 2, choose Li, minus R minus 2 minus Li, choose Lj. And then we can substitute whatever this number is. What is this number? So number of permutations of I3 to IR. So what is this number? I know that in this I have Li many I and Lj many J, and the rest I don't care about. So the number is R minus 2 factorial over Li factorial, Lj factorial, and some other combinations, right? Downstairs, I know there is one I, one J. I also have Li many I's in the rest and Lj many J's in the rest. So the downstairs give you R factorial over Li factorial, Li plus 1 factorial, Lj plus 1 factorial, and the same star. I don't care about what happens to the other numbers, right? So you get you get Li plus 1 times Lj plus 1 by R minus 1, right? So put the R minus 1 here, throw in Li plus 1, Lj plus 1. This R gets cancelled with this, and R minus 2 factorial gives you R minus 1. Okay? What happens to this sum after I do this? So I know there are Li many copies of I in these things. So I will get Wi to the power 2 Li, Wj to the power 2 Lj, and there is an unrestricted sum after that, right? So the point is these Wi's are unit vectors. So their squares define a probability distribution. So the remainder of the sum gives you this, right? Probabilistically, this is just the expectation of a multinomial, a multinomial expectation. This is just the expectation of x plus 1 into y plus 1, where x, y, z follows multinomial with R minus 2 bins, and the probabilities are given by Wi square Wj square and 1 minus Wi square minus Wj square. Okay. And this can be easily computed. You get a degree 4 polynomial in Wi and Wj. Maybe just write down the polynomial expansion and then I'll take a break. So this turns out to be 1 over r minus 1 plus r minus 2 over r minus 1 plus times Wi square plus Wj square plus, so these numbers are precisely these constants in the answer. R minus 2 times r minus 3 over 1 Wi square Wj square. Okay. So at the end you get a degree 4 polynomial in the coefficients quite miraculously. So you can do this type of multilinear calculation for every possible covariance pattern. Okay, there are 7 of them. Okay, and then you match that with this. They exactly match somehow. Okay. The crucial point here that enable this is that W is a unit vector, so you can interpret the coordinates as probabilities. That connection completely breaks down if I contract along, let's say, different directions. That's right. Then you don't get this type of squares, and this probabilistic interpretation completely breaks down. And that's why we are not able to do it yet for general contractions. Okay, so let's maybe take a break and that is this. Yes. Yeah, so I just wanted to give you a flavor of some beautiful exact representations that come out of this GOT contractions. So these are only proved for GOT. So if you can prove it for general tensor, that would be quite nice. None of these are proven to be universal, at least these results. Okay. And so previously, people obtained some of these results using very complicated free probability techniques, but this exact representations basically gives you a two-page proof of all these things. Okay. Uh, Well, I'll briefly tell you about the mixed contraction setting before going to after that I will define a generalization of the Stieltjes transform that I have promised earlier. Um, so what happens for mixed contractions? So I'll just write down the corresponding representation. So suppose R is fourth. We have a fourth tensor. Okay. And you have two directions now, U and V. G is still a GOTE tensor. Now we are interested in the mixed direction contraction. U and V are different. So this is the exact representation for of the covariance structure. Okay, so rank 4 plus a GOE part. This is only for R equal to 4 and 2 directions. Right? What are these U's and V's? Capital U's and capital V's. They are no longer independent. At least the V's are no longer independent. Well, there are two of them, so anyway. So U is a standard normal, and V1, V2 are jointly Gaussian. With the following covariance structure. Okay. So this is the complete explanation of the covariance structure of this matrix. And since we do not have any interpretation like before of these weights here as probabilities, multinomial probabilities, this is proved completely by brute force calculation. So it would be really nice if there is a nice explanation of this representation. And so how do you generalize it to general contraction? So so this is just for R equal to 4. How do you do it for general R minus 2 directional contractions? Right? And what would be the corresponding representation? We think there is a rank 2R perturbation added to a GOE would explain the covariance structure, but yeah, you don't know. Okay, so that's all with tensor contractions. I just wanted to highlight that because they are somehow beautiful objects in the sense that every distribution that you know in random matrix theory, they show up in some form of other. Semicircle law, Tracy-Whedon law, those mixed laws, even the random regular graphs, LSD, all of them show up. Okay, so now I want to completely move on to a different topic. So we have defined these eigenvalues. Yes.
You mentioned the case already.
Yeah, so these are random matrices, so you can use standard free probability techniques. But yeah, but that's important. So Charles Bourdanov and his student Remy Bonin, they are developing a parallel of free probability for tensor at the tensor level. And we expect that there should be some contractions going on there, and that would take you back to the domain of usual free probability. Okay? But that is still at a developmental stage, so we don't have all the there. Yeah, so the fact that this will converge to a semicircle law with this as the covariance, that you can prove using usual free probability, but that is much more complicated than this representation. Once you have this representation, you have access to much more things. You can talk about eigenvectors, you can talk about the largest eigenvalue, etc., etc. That's not possible with the usual free probability. Um, So let's recall. So the goal is to define. So as I said, so there is no. So why to have why is random matrix theory so well developed? So one fundamental result is that if you have a matrix AN, you can look at the nth power of A and take the trace that is same as the sum of the eigenvalue. The nth power of the eigenvalue, right? There is this identity. So this identity allows you to write down the moments of the spectral measure as certain polynomials in the entries of the matrix, which you can control then using combinatorial techniques, right? So that analogy or this connection between the traces of moments of the matrix and the moments of the spectral distribution, that breaks down for tensors. There is no known connection. That's why tensors are hard. So nevertheless, so Rusvan Gurau recently defined an analog of the Stieltjes transform that I want to highlight, which is an exact generalization of the Stieltjes transform for random matrices. So let's recall the Stieltjes transform. So let A be some matrix, right? And mu A is the spectral measure of A. Spectral measure of A. So then the Stieltjes transform of this measure recall that we defined it to be this integral. Okay. So Gurau defined an analog of that for random tensor. So I'm going to write down the corresponding transform, and I'll try to explain what it really means. So now you have a tensor T, order R tensor. This is the transform R T of Z. It might look a bit scary, but we'll try to explain what it means. So maybe Z is a bad notation for partition function here. So maybe I will write capital theta. One over Z, then an integral of a certain Gaussian integral. So this is our familiar friend, the multilinear, the polynomial, not the function, multilinear functional, the homogeneous polynomial that you get. If you set every coordinate of the multilinear functional equal to one vector, and sorry, this is plus, and you have a Gaussian density. Okay. So he defined this transform, which is supposed to be the analog of the Stieltjes transform for random matrices. Okay. Yeah, so that's the first question. It's not necessarily even convergent, right? You have a Gaussian integral, this will blow up. This is only defined as I have written for, let's say, on the complex line -0. It admits an analytic continuation to C minus R. But let us first see, I will try to explain what that beast really does. But let's try to see that this is actually a generalization of the Stieltjes transform for matrices. So for R equal to 2, this should give you back the Stieltjes transform. So I'll do again, I'll do a heuristic computation. To justify this, you need some complex analysis. But anyway, this will at least tell you why it's a generalization. So for R equal to, so claim for R equal to 2, RT of Z is actually equal to the Stieltjes transform of the spectral measure of T. T is a matrix for R equal to 2, so I can talk about the spectral measure is the Stieltjes transform of the spectral measure. Okay. Sorry? Theta is a partition function. Yeah. So you have to normalize that. So I write down what this is. So theta Z is one over Z Mhm. And then you have the Gaussian density. Just the partition function corresponding to that integral over here. This should look a bit familiar. Does it look familiar? Like this type of expression, we have seen this expression before. This is like the Hamiltonian of the spherical spin glass, right? So there Z or the spin configurations were restricted to the unit sphere, right? And the base measure was the uniform measure on the unit sphere. I am writing a Gaussian version of this. Now my spins are real vectors, and the base measure is the standard Gaussian, right? And the inverse temperature is now a complex number. Okay? So this is really this is called the Gaussian spin glass. Okay? And this transform in some sense is just the second moment of that measure. It's not a measure, but whatever that object is, it's the second moment of that. So this is the partition function. Of the spins are real vectors. Okay, so let us try to let us try to see why this boils down to the Hilliard's transform for matrices. So let us look at that partition function first. Theta of z, this is just this integral over 2 minus phi square over 2, and then you have the normalizing factor. So look at this expression. I am in R equal to 2. So both of these are really quadratic forms. So this is like phi transpose phi, this is phi transpose T phi, right? This is a quadratic form. So I'll write this as this whole thing as a new quadratic form. And you can see the appearance of the resolvent now. Right? This I can write like this. This is a quadratic form. If R equal to 2, this is a quadratic form. So I just write it in this way. Right? I minus tau inverse.
Because if it's a non-square, then it goes down one at all.
This is just the density, right?
Yeah.
I minus tau by z. Tau is, oh, I see. I put the bracket the wrong location. You're right. That is correct. Okay. So with that, again, pretending that, okay, so now pretend that z is real. and this is very large, then this is a positive definite matrix. So this is really a Gaussian density, right? Um, so therefore, R Tz is really 1 over n, the expectation under this standard normal, this normal. So the covariance matrix is basically this, right? If Z is real and large, this is a covariance matrix. This is positive definitely. Is the second moment of that Gaussian, right? So this is precisely 1 over nz trace of I minus 1 over z tau inverse, which is the resolvent. Well, this is not a proof because my object is defined only on, is defined analytically, defined on C minus R, and there I am taking R to be large real number. This is just a heuristic, but you can make this this into a precise theorem using some complex analysis. So that really matches the Stieltjes transform outside the spectrum of T. Okay? In this sense, that gives you a generalization of the Stieltjes transform in the case of tensors. Right? There's also something going on. You see, this object that we see, this is precisely the thing that we maximized over the sphere to get to show the existence of a Z eigenvalue, right? That is this is the sphere, the Lagrange multiplier. Remember that. So this is the Z eigenpairs. They are critical points of this Hamiltonian. That's as far as the connection goes. We cannot really still write down this as the, for instance, as the Stieltjes transform of the spectral distribution of the Z eigenvalues. We only know that the Z eigen pairs are critical points of that Hamiltonian. That is the only connection that we have. Okay. So now here is another theorem which shows that this R tau z is in fact a Stieltjes transform of a probability measure. That is not guaranteed, right? I mean, for the matrices is guaranteed, but this is in fact the Stieltjes transform of a probability measure. Again, the proof is not easy, so I'm not going to do it, of a probability measure. But you can call that probability measure the spectral measure of a tensor by analogy to the matrix case. The point is we don't know what those what does that mean? Whether it is connected to any notion of eigenvalues, etc. That is still not known. Okay? But probability measure mu tau, which we may call the spectral measure of the tensor T. Yeah. So it is not known. So let me highlight this. So this, if you can find out some notion of eigenvalues which is connected to this, that would be a big thing. So it is not known if mu tau is the spectral measure of any notion of eigenvalues. Hmm? No, we don't know that. Um, but you can study
Size of the output of the.
we don't know that, so yeah. Yeah, but we don't know that, for instance, it is compactly supported, but we don't know that whether the right endpoint will converge to the right endpoint of the limiting. But you can ask this question, this at least this part has been proved, that if you take those GOT tensors we looked at, consider the spectral measure in this sense of those GOT tensors, let n go to infinity. That will converge to a probability measure, which is a generalization of the semicircle law. Okay? To define the moments of this spectral measure, so this is the kth point of the spectral measure. I will denote it by I of tau, ik of tau, ik of t, sorry. It turns out that this IKTs, like the matrix case, these are polynomials in the entries of the matrix. And they are basically trace of a to the power k if you give me a matrix. Right? So for r equal to 2, these objects ik t, they are precisely the trace of the kth power of t for matrices. And since these are polynomial in tau, there is a combinatorial interpretation to them. Just like trace of t power k has a combinatorial interpretation, they have a combinatorial interpretation. The combinatorics is much more complicated. You need a gadget called combinatorial maps. Okay, I'm not going to go into that, but this can be analyzed combinatorially, and you can show that. Okay, so let now t equal to that GOT tensor G that I described earlier. And if you normalize it by n to the power r minus 1 by 2, then these moments of the spectral measure, they converge to what are called first Catalan numbers. Okay, so if Rm is 1 over R m plus 1, Rm plus 1 over m. Okay. These numbers are called first Catalan number. These are some generalizations of Catalan numbers that count non-crossing pair partitions. Okay. And they determine a compactly supported probability measure. That's the generalization of the semicircle law in this setting. So yeah, so the limit moments determine a probability law, which we denote as mu infinity r. And so yeah, so this, yeah, nowadays this is called the Wigner-Grau law, the generalization of the semicircle law. And the corresponding Stieltjes transform, so Grau's transform, that converges to some r infinity z, which satisfies the first. There are two ways of proving it. You either do it combinatorially like this, or you directly prove the convergence of that transform. Okay. So you can show that that transform pointwise converges to some limit object, which is actually also a Stieltjes transform of this law. And it satisfies the following functional equation. So g to the r minus 2 r infinity to the rz minus drz plus 1 equal to 0. Okay. So all of this was done by, in a paper of Grau in 2020. And recently, so this was done mainly via an analytic machinery. So Grau actually showed that that transform converges to some limit object which satisfies this functional equation. And from here, you can recover the limit description. So recently, Bonin actually proved that you don't need GOT. You can have mean zero variance on other random variables as well. So universality by means of moment method. So he actually proved that these moments converges to the corresponding first Catalan numbers. So this result is due to Bonin. So this is only for GOT. And recently Bonin very recent, it's 2024 plus universality. Okay. And turns out there is a very nice hierarchy going on. This law is at the top. You take this GOT tensor, contract it along j many directions. Okay. So we looked at the j equal to r minus 2 case when you get a matrix. We get the semicircle law, right, at the limit. If you don't contract, you get this Wigner-Grau law, right? If you contract along j directions, right, j is between r minus 2 and 1, then you again get this family with a different parametrization. Okay, so there is a hierarchy of laws going on. At the top level, you have this Wigner-Grau law. If you contract by one direction, you get a lower dimensional tensor, right? A lower order tensor, r minus 1 order tensor. That will also have this Wigner-Grau law with a different parameter. All the way down to this r minus 2, which we have proved earlier. Mixed ones are not known yet. That's a good point. Mixed ones not known yet. And as he was asking, we don't know whether the right endpoint of the support of that empirical law converges to the right endpoint of the support of this Wigner-Grau law. Right? Yeah, I think I'll stop here because that's what I wanted to say about this. Okay.
Thanks, from everyone.
Oh,
So I the phone set up.
He wants to have the last word. He wants to have the last word.
Computer. So, I mean, it's a charity started I think in 2006. And I just realized that it's about to enter the adult. So it's a 70th and I took on the SIR going on, it should enroll in for the serious election and things like that. And it's also a time can the organizers. I've been with it for like several years at the beginning. It's a hard work, and it's really nice. So first of all, and the speakers, both the talks were accessible and informative. I mean, my experience, it's a very difficult thing to do. Like, I mean, keeping it accessible and letting people learn something new. People generally go wrong on island nation, but this time both the talks were nice that way. So thanks, Nathan. And this year we had a new location, IIT Madras. And so the first student volunteers.
Cheat sheet.
I can be hard. Zoom.
Then don't shout.
Oh, okay. Yeah, I mean, I'm feeling bad. I mean, this semester my students said like I need a microphone. I mean, that's the worst review I got for my teaching. Anushka Chakraborty. Where is Anushka? Yeah. You can wait where they can you all. Sripati Majumdar. Kuldeep Pal. They can take your photos together. That would be nice for them. Ravindra Shah. The student volunteers are the real backbone of the organization. I mean, I think the organizers themselves will also agree. Like, I mean, you have the bosses, you know who the boss is, and then actually who do the work. So they are the student volunteers. So big platform. Thank you. And now the local organizers, local faculty, Shubhajit, Keshav, and Varun, please. And finally, the big boss, Shiva Atreya. We started like, please. Three of us started. I mean, one is missing today. Two of us are here.
We started it in 2006, and Shiva was one of the first speakers. I mean, one of the two first speakers. He did the organization, he did the speaking, he did everything like he always does. And most importantly, this LPS sort of was lost its steam during the COVID years, most of the usual side effects of COVID as always. And Shiva took up the job of reviving it and first doing it at ICTS, his new hometown, and after leaving us from ISI, and then he's now doing it in IIT Madras also. So a big thanks to Shiva. And the last word to Shiva.
I mean, the organizers is one thing, but I think I mean, an event especially of this scale, we had support from many pillars. So I'd like to really invite the staff from the physics department, from the maths department, and from our coffee providers for the entire seminar, because that's also as mathematicians convert coffee into theorems. So please, if you can come up, everyone will. வாங்க. I think the local organization is one thing. We really could not have done it without our multiple pillars of staff, including Dreams Photography and NPTEL for handling the live streaming and the photography of the event. And although they're not in the room today, I also want to give some acknowledgement to the global engagement team of IIT Madras. They were present during the dinner. I don't know if any of you got to interact with them. So you have them to thank for the ID badges, the note site. So it's fairly important work, and it's tough work. And they're the ones who made this process far smoother. And I mean, so a meeting of this size really was quite easy. It became quite easy to organize thanks to all their hard work. And a special thanks to the physics department as well for giving us a home for this week. Because this is, I think, very unconventional for this institute. So we really want to acknowledge this. And any way we can reciprocate the favor in the future, we'll be more than willing. So please give them a big round of applause. Oh, and we'd really like to acknowledge our sources of funding, or our sources of sponsorship for this event. So it is IIT Madras Global Engagement, and the IIT Madras Alumni and Corporate Relations Office. So it's a round of applause for them as well.
I have one last thing before we close. The next LPS will be from November 29th to December 5th week of 2026 at IIT Kanpur. And we are trying a different experiment. We'll have LPS for 5 days or 4 days, and then a 2-day conference adjoining it after that. And Dutika could not come to this meeting. She's traveling, but she'll come online. I don't know. You want to say anything?
Am I audible? Can you hear me?
Yeah.
Okay, excellent. So Supriyo Bharat, Professor Supriyo Bharat from IIT Kanpur is also online. Yes. So indeed. We're very excited to be hosting the 18th LPS at IIT Kanpur. So this will be in December in 2026, as Shiva mentioned. We've sort of started planning the logistics, but nothing's completely finalized, obviously, yet. So we'll share more details in the first few months of the year, and keep a lookout for the website, and we'll advertise as well. We do hope that I know, and I've heard that this event has been a great success at IIT Madras. So we hope all of you all can also join us in IIT Kanpur and make the 18th version also a fantastic success.
Thank you, Veda. Bye, Veda.
Bye.
Give your name tag. Oh, okay.